This video is all about independent events. A coin is flipped and the first toss shows a head. What is the probability of the second toss being a head given that the first toss shows a head? Well, hopefully you know the answer intuitively to this one. The answer is a half, because each coin toss is independent of the last. That is, what's happened before doesn't actually affect the outcome of the next coin flip. So even though you know that the first coin toss is a head, the probability of getting a head the second time around is still just 1 in 2. Let's work that out mathematically. The probability of A is the probability that the first toss is a head, and that equals a half. Probability of B, the probability that the second toss is a head, that's also a half. The probability that we get a head followed by a head, so A and B, is going to be, if we look at it in a tree diagram, head followed by a head, half, half. That is going to be a half times a half, which is a quarter. The probability of A given B is the probability that the second coin toss is a head given that the first coin toss is a head. So the answer to this needs to be a half. So the probability of A given B is the probability of A intersect B over the probability of B. That's just the conditional probability formula. And we've worked out A intersect B, it's a quarter, over the probability of B, we worked that out as well, that's a half. All right, and that is, in other words, 0.25 over 0.5, which is 25 over 50, which is a half. So the probability of the second toss showing a head does not seem to be affected, or not seem, but it isn't affected by the outcome of the first toss. And we call these events independent. So basically the coin doesn't know what came up before. Or if I told you, hey, would you like to know what the results of the last 5 coin tosses are? You should say an emphatic, no, I'm not interested. Saying a tail is due, or just one more go, my luck is due, is called the Gameless Fallacy. And I'm afraid we've all probably said that. Even very talented mathematicians have said this, and we've fallen for what is known as the Gameless Fallacy. So 2 events A and B are independent if the occurrence of one event has no effect on the probability of the other. That is, that the probability of A given B has happened is just the probability of A, i.e., knowing that B happened has no effect on the outcome of A. So we already know that the probability of A given B is this, the probability of the A intersect B over the probability of B. Now I know that when events are independent, the probability of A given B is just the probability of A. Okay, that's just this statement here. And I know that probability of A given B, that thing there, is also that. So it is therefore intuitive, or not intuitive, but it makes sense that the probability of A equals the probability of A intersect B over the probability of B. And this, we can forget this part of it. This part here can be transposed, so we can multiply by the probability of B on both sides. And we get this formula here. And this is the probability, or the independence events check. Okay, or this is the way I check for event independence. That is, if the intersection of A and B is equal to the probability of A times the probability of B, then the events are independent. So let's try it on a couple of questions. 500 people were questioned and classified according to age and whether or not they regularly use social media. The results are shown in the table. Is the regular use of social media independent of the respondent's age? So what I can do is basically just choose a portion of this, and there's really 2 ways of doing this. I can test the probability of A given B is equal to the probability of A. Let's just do that. Like, what I'll do is I'll test it on probability of a yes, given that they are less than 25, is equal to the probability that they are probability of a yes. All right, so let's do the check on this one. So the probability of yes, given that they are over 25, is 200 over 240. And I'm checking to see whether that is equal to the probability of a yes, which is 300 over 500. 4/5 equals 3/5. No, it doesn't. No, it doesn't. No, it doesn't. Therefore, not independent. That is that there's some sort of dependency. That is that if you're under 25, you may be more likely to use social media or less likely. But knowing that a person is under 25 means that the probability that they do use social media depends on the age. Now you can do this the other way, which is the probability of A intersect B equals the probability of A times the probability of B. So we can check it this way as well. So this is the probability of yes and less than 25 equals the probability of yes times the probability of less than 25. And A and yes, that's going to be 200 over 500, 2/5. 200 over yes, 500, 2/5 equals the probability of a yes, which is 300 over 500 times less than 25, which is 240 over 500. Cancel that. So that's going to be 24 over 50, 12 over 25. So that is 2/5 equals 3/5 times 12 over, that's going to be, what is it, 36 over 5 times 25 is 125. So they're not the same as each other. So they're not the same as each other. They're not the same as each other. Therefore, we say that they are not independent. There's really a couple of ways to do the check. To use this statement here, the probability of A given B is just the probability of A, i.e. knowing B does not help us. Okay, we check whether that's the case. If it's not the case, then they're not independent, or we use the independent events check, which is the intersection equals the probability of A times the probability of B. So two ways. Right, an experiment consists of drawing a number at random from these numbers. And A is this set, B is this set, and C is this set. So let's get the probability of A. 4 in 8 is a half. The probability of B, 4 elements out of 8 elements, which is a half. And while we're at it, we'll just get the probability of C, which is 3 in 8. All right, to do the check here, we'll go the probability of A intersect B is equal to the probability of A times the probability of B. Okay, the probability of A intersect B. So we've got a 1 and a 1 and a 3 and a 3. So this is 2 in 8 or 1 in 4. Probability of A is 1 in 2, 1 in 2, 1 in 4 is the same as 1 in 4. Therefore, these events are independent. Okay, are A and C independent? All right, so we've got the probability of A intersect, not B, intersect C is equal to the probability of A times the probability of C. Okay, A intersects C, so we've got, the only thing that they've got in common is this 4 here. So we've got a 1 in 8 on the intersection. A was half, C was 3 on 8. 3 on 16, they're not the same, they're not the same, they're not the same. So therefore, not independent. All right, are B and C independent? So we'll go probability of B intersect C is equal to the probability of B times the probability of C. So probability of B and C, so that's the probability of the intersection. There's no elements, it's the empty set. The empty set is this thing here. And so we're going to say that the probability of getting an intersection is 0. There's nothing there, so you can't get it. Is the probability of B, which is 1 in 2 times 3 in 8. And we know that 0 is not equal to 3 in 16. So so therefore not independent. Now this example is good because if there's no intersection, what that means is that this is what the Venn diagram looks like. So no intersection means that these events are mutually exclusive. Okay, and what we need to be aware of is that just because events are mutually exclusive doesn't mean that they're independent. In fact, they're two completely different concepts or two completely different ideas, often confused. Okay, so we can see here that these events are not independent or dependent on each other and mutually exclusive. So again, to summarize, mutually exclusive doesn't mean independent of each other. Okay? And the only time this is actually going to happen where events are mutually exclusive is if the probability of one of these events is 0, because then we'd get 0 times that. But if that's the case, why would we be looking at the probability of something where one of the events is impossible? So it just doesn't come up. Okay, so it's important to note that independence is not always intuitively obvious, and in many cases there is an obvious physical independence between two events in that each has no effect on each other. For example, rolling a die and tossing a coin, and the probability of a head is not affected by the result of the roll of the die. But in some cases there's no obvious physical independence between two events, and yet the two events are mathematically independent. For example, rolling a dice and considering the sum. And this is a great example of it. And really, the only way to do these ones and to do that with any confidence is to do the test. It's very difficult to see whether things are independent or not independent. So suppose we roll a dice twice and define the following events. The first roll shows a 4. So that's all of these options here, which is 6 in 36. There's a 1 in 6 chance of that happening. Second roll shows a 4. That is these events here. 4 is second. Okay, so that is going to be 6 in 36 or a 1 in 6 chance. Sum of the numbers showing is at least 10. There's the at least 10s. 3, 5, 6. 6 in 36. 1 in 6 chance. Are they independent? Let's check. Okay, so let's just use some intuition. So A and B, first roll shows a 4 and second roll shows a 4. Well, these have to be independent, because if I told you, hey, I'm rolling a dice, what do you think is going to come up? And would you be interested to know what the last roll was? The answer should be an emphatic no. I'm not interested, because the events are independent. It doesn't matter what's happened before. What matters is the result of this roll. But let's just mathematically see whether this is the case. Right, the A and B, so 4 and a 4, that's this event here, and there's a 1 in 36 chance of that happening. Probability of A times the probability of B. So these events are independent, which we knew. So this one here is A and C. So let's just have a think about this and see if we can do it intuitively. The first roll shows a 4 and the sum of the numbers showing is at least 10. So intuitively, I say that these are dependent events, because if I said to you, we're looking at the sum of the numbers showing is at least 10, would you be interested in knowing the result of the first roll? I think you'd probably say, yeah, I am. But in fact, let's just see what happens when we try to show that mathematically. Probability of A intersect C is equal to the probability of A times the probability of C. Okay, A we already know is a sixth, C is a sixth, and first roll showing a 4 and some of the numbers showing at least 10. First roll shows a 4 is this one, and some of the numbers is at least 10. That's the only condition, and there's a 1 in 36 chance of that. So that is 1 in 36 equals 1 in 36. Therefore, these events are independent. Now, this is one that is a little obscure, and if you asked me, as I was walking down the corridor quickly, could I have a look at this and see whether they are independent or not? I couldn't with any confidence say. In fact, I would tell you to do the test to check, because I don't know. So why does this happen? Why are they independent of each other, given that it seems so obvious that knowing the first roll being a 4, like just say I said it's a 1 first up, sum of the numbers is at least 10, would you be interested in this event, or knowing what happened first? I would sort of go, yeah, you would be, wouldn't you? You certainly would be, but in this case, no. So why is this the case? So the notes will go through and walk you through some like an explanation of this, but the best example to do is to just take another one, which is introduce event D, which is the sum of the numbers showing is at least 9. Right, so the sum of the numbers showing is at least 9 adds these ones, okay, which is another 4 events. So that's going to be 10 in 36 or 5 in 18. So let's check whether they are independent or not. Probability of A intersect D is equal to the probability of A times the probability of D. Okay, so A was 1 in 6. This one was 5 in 18. And A intersect D, sum of the numbers showing is at least 9. 4 is rolled first. So this is at least 9. And this one also is at least 9 with a 4 rolled first. So that's 2 in 36. That's 1 in 18 is the same as 5 over 60, 6 eighths of 48, 5 over 108. Now, they are in no way, shape or form equal. So what we're going to suggest here is that these events are not independent. That is, this outcome here depends on the first roll. Okay? So why does this one come up as not independent and the previous one does? Well, the best answer I can give was an explanation I saw by a professor over at, or a lecturer I think he is, over at Adelaide Uni. And what he said was that for independent events to occur, the Venn diagram must overlap or intersect in a very specific way. Those were his words. So I've just said here, sometimes even when things feel not independent, they can, because they overlap in a particular way. And that's what happens with the first one. This example here of first roll 4 and some of the numbers being 10 overlaps in such a way that we get that 1 in 36. The overlap in the second example is 2 in 36, and it just doesn't work that way. So other times, things that feel not independent actually are, because the overlap doesn't occur in a specific way. Okay, so the overriding thing I'll say to you is, if you're ever in doubt, don't use intuition, use the test. Okay, suppose that the probability that a family in a certain town owns a television set is that, owns a station wagon is that. If these two events are independent, find the following probabilities. A family chosen at random owns both a television set and a station wagon. So we're going probability of a television set and a station wagon. What's the station wagon letter? S. And I know that the events are independent. Okay, so basically they're suggesting that if you know that someone owns a television set, that information is going to be of no relevance if you're trying to work out the probability of them owning a station wagon. Okay, so all we'll do is go 0.75 times 0.25. So that equals 0.1875. A family chosen at random owns at least one of these items. So that's this will be the probability of T only. So this is basically what we're looking for here. At least one of these items means the union, because it means not neither of them. Okay, the best way I can think of doing this one is to probably pop the information we've got in a Carnot map and try to explain from there. So to do a Carnot map, or one of these tables here, it's a 3 by 3. T, T naught, S, S naught, 1. Now the intersection we just found out is 0.1875. T is 0.75. And S is 0.25. Now at least 1 means the intersection, which is this part here, plus S and not T. So we need to find out what this value is, and we need to find out what this value is. And these three combined give you the union. On the diagram, or on the Venn diagram, we'd be looking at the intersection, T only, and this part here, S only. So the union is what we're talking about here. Or we could just calculate this value here and remove it from 1, and that would also suffice. I'm not sure what's the fastest, so I'm just going to do it this way. So we're going to go 0.25. I'm going to use the calc on this one. So this one here is 0.0625, and this one is what am I doing? 0.75, take away 0.1875, 0.5625. So all we'll do now is just add them together. So that plus 0.1875. So this one here is 0.8125. So there's one way of getting it. Another way of getting it would be 1 take away the probability of this item here, which is not T and not S. So we could work this out, which would be 1 takeaway. I think this is going to be a quick way. I might just stuff this up and have to re-record this, but I'm going to take a risk here and go 0.75 times 0.25. Yeah. So if you multiply those two together and remove it from 1, what you get actually is this union part here. Okay, so yeah, that's that answer there. If you're not too sure about how I got that, just stick with the Venn diagram over here, or the two-way table. You can't go wrong. Okay, so as alluded to before, if events are independent, they cannot be mutually exclusive unless the probability of one event is 0. And again, why would we be bothering? So why, if event A and event B are mutually exclusive, then the intersection is this thing here, the null set, or the empty set. There's nothing in it. So in testing for independent events, what we do is we test this. To make this true, either probability of A has to equal 0, or the probability of B has to equal 0 for something that's mutually exclusive to be independent events. Okay, and this is not going to happen. Why would we be testing it? Okay, so here is the final example from the Year 10 probability test a couple of years ago. So events A and event B are independent. Okay, important to know. The following is an incomplete two-way table. Show that the probability of A intersect B is 0.09. So we can fill that in straight away. And we know that for independent events, the probability of A intersect B is equal to the probability of A times the probability of B. And we know that the probability of A is 0.3 and the probability of B is 0.3. 0.09 as required. Hence complete all missing parts of the two-way table above. I think that's right. Yeah. Probability of A intersect not B, or A only. straight off the two-way table, 0.21. Probability of A given B. So the probability of A, so it's that given that. So the sample, so B has happened, so the probability of B is 0.3, and the probability of A intersect B is 0.09. So it's going to be 0.09 over 0.3, which is 9 over 30, which is 3 in 10. All right, so there is independent events, and there's your questions.